Cool. Hello, everyone. Good to see you again. Today is going to be a little bit of a special lecture because we're going to talk about a topic that is so new that I'm pretty sure this is the first lecture that anyone has given up this. I'll be honest, these slides are not as polished as some of the other ones that I have presented so far because I have made them on relatively short notice. But I thought that because this development is quite significant, it would still be worthwhile. It's better to talk about this in a less polished way, but sooner than talk about it not at all. So we're going to talk about it today. It's very exciting. So summary of the last lecture. In the last lecture, we discussed the beginning of inverse graphics or differentiable rendering, and we discussed two basically different differentiable rendering algorithms. As a brief reminder, what is rendering? Rendering is a function that goes from a 3D scene and a camera pose to an image. Then we defined inverse rendering as obviously the inverse of that. So we go from an image to the 3D scene and the camera poses that of these images. And then we said, oh, but wait, this seems like a very hard problem. And we kind of already know how to get the camera poses from images, which is structure for motion. So actually the way that people usually treat inverse graphics today is in the setting where we assume that we have the camera poses of the images already. And then inverse graphics reduces to the problem of we have images, we have the camera poses, let's recover the 3D scene. And this is changing. This is what happened. This is in the process of changing. Okay, somehow it just jumped ahead like 50 slides. I don't know why. So this is in the process of changing, and we'll talk about that further a little bit at the end of this course. But right now, this is still the current paradigm for inverse graphics. And then, just as a brief reminder, how did all of these algorithms basically work? We always started in the last lecture. We said, okay, we have some kind of 3D representation. Could be a voxel grid or could be a neural field, right? So voxel grids basically take the scene and they discretize it, and in every voxel you store some information about the scene. Could be the density and the color, for instance. Could be the signed distance. Then, like neural fields, basically parameterize it as a neural network. So you have a neural network that takes a 3D coordinate as input and maps it to the RGB color or the density or maybe the signed distance at that coordinate. So that was part number one, the 3D representation. Any questions on that? Good. Then we talked about the actual differentiable rendering process and the different differentiable renderers. So we said, okay, assume that you have a scene representation. Let's build a renderer, a differentiable renderer. What that allows you to do is it allows you, assuming that you have the camera poses and the images of a scene, you can just render out. You can use your scene representation and your differential renderer to render the scene representation from exactly these camera angles. Then you compare the renderings to the ground truth images that you captured. You compute a loss, like a reconstruction loss, and then you can just, using differentiable programming, optimize the whole thing end to end to like fit the 3D scene, right? So that is the key idea of differentiable rendering. Any questions on that? Please just interrupt if you have any questions. Cool. And then we discussed like specific implementations. We discussed specifically two. And we said basically the way that these differentiable renderers for these kind of volumetric representations work is that you shoot a ray from the camera and then you sample lots of points along the ray. And then you have some way of, then at each of these points you'll sample your scene representation, and then you'll have some kind of algorithm that integrates information across these samples. Oh, that, okay. And we discussed specifically sphere tracing and volume rendering. Let me just briefly refresh you on volume rendering because this is going to come up again today. So this was the overview slide that they converged to at the end. And if you have any questions to this, now might be the time to ask them. So what was the key idea of volume rendering? The key idea was to parameterize the scene as a radiance field. Radiance field means at every 3D coordinate, the scene representation, like the voxel grid or the neural field, maps that 3D coordinate to a color, which is the radiance, the amount of light emitted at that 3D coordinate, as well as the density. So it's basically modeling the scene as a cloud of particles, where every particle is emitting radiance with some color, right? So that's the model of the scene. And then it's defining a rendering algorithm on top of that representation, on top of that model, that allows you to render images. And the way that rendering algorithm worked was exactly, you take the camera, you position it in your scene, right? Imagine the scene is your voxel grid. Like this room here is like parameterized as a voxel grid. You position your camera in this voxel grid, and now you shoot a ray. And now what you say is, basically what you want to do is you want to compute the color that is observed by that ray, assuming that the scene is made out of these particles that are all emitting radiance. And this is exactly what volume rendering is. Volume rendering is exactly that forward model. And the way that that is done is in the continuous model, basically to say the density at every point is interpreted as the probability that a light ray ends at that point in space, right? So for instance, if you have a particle floating in space, if that particle has a very high density, then it means that if a light ray intersects with that particle, it's very likely to just end up at that particle, right? And so because this probabilistic interpretation basically allows you to formulate the color observed by a ray as an expectation of all the colors along the ray. You basically say, I shoot the ray, and for all the particles along the ray, I basically take the expectation, what is the probability that the light will get up until this point, and then that is the weight for the color at that point, and then this expectation, this integral, is going to give us the color for that ray, right? And then the question is, this is of course like a continuous integral over this like continuous like function. Now, how do you compute it in practice? Because some question asked, well, this integral is this analytical? No, the integral is not analytical. You can't compute this analytically in general. We will actually hear about like very special cases where you can't compute it analytically like later, but not today. And in practice, what you do is you say, well, I place my camera in the scene. I assume a near plane and I assume a far plane, and I say everything that the camera can render is between this near and far plane. And it could make sense to place, in theory, you could place the near plane at the camera itself, but there are practical reasons for why you don't usually do that. So you usually say, oh, I never touch, with the camera, I never touch like something. Generally, when you have an expensive camera, you don't like to put it directly into something, right? So maybe you place the near plane 20 centimeters away from the camera, you place the far plane at some distance away, you say that contains the scene that I want to render, all the parts of the scene that I want to render. Then you take your ray, and within these bounds, you discretize the depths. So you discretize it into bins, what you see here on the right-hand corner. And then we're going to say we're going to approximate this integral. And this is important. We're going to approximate this integral via a sum of segments. We assume that in each of these segments, the color and the density are constant. And then it turns out that there is a relatively simple way of just writing down like a weighted sum that gives you the color of the ray. Any questions on that thing from last lecture?
Object that is actually not physically transparent. So what are the colors inside the object into your space?
Great question. I'm not quite sure if I caught the question exactly right. So you're asking for an object that is opaque, so not transparent.
Yeah.
What are the colors inside?
Yeah.
Yeah, that is a great question. So usually you would say that the colors are basically undefined. Right? For like if you take a video of this piano, like there is no way for you to reconstruct what is inside this piano, right? You just don't observe it. So it's just undefined. It'll be noise.
It's totally random.
It'll basically be totally random. It'll be, well, it might not be totally random. Basically, there's no easy answer to this. It's going to be like usually it ends up looking like some gray clouds. It'll look like nothing in particular. So if you delete this outer shell that is opaque, inside the object, usually there's like some like semi-opaque cloud of artifacts. Is that a fair? Yeah? Okay, good. It's actually a good question because that relates to something we're going to discuss today. Okay, other questions? Okay, so this is a good forward model, and we discussed one reason why this forward model is particularly good for inverse graphics. And maybe why is this forward model particularly good? Why is this renderer particularly good for optimization via gradient descent? Can someone recall? Like, what is the difference of this, for instance, versus doing differentiable, maybe mesh rendering? Yes?
You can remove density and reappear it somewhere else versus having to move. You don't have to move through space to move an object. Like, you have to optimize through 3D coordinate space to move it.
Right. So in other words, what you're doing here, by taking all of these samples along the ray, what you're allowing your optimization algorithm to do is it can basically just conjure up objects and vanish them again at any point along the ray by just increasing the density along the ray or lowering the density again. And if you think, what does the gradient mean, right? If you take the derivative of the color with respect to all of the points along the ray, what you want from a good optimization algorithm is that that derivative is never vanishing. Like if the derivative of the color of the final cover that you render relative to any values along this ray is 0, then it means that your optimization might get stuck in a local minimum. And because this weighted sum shenanigans, if you initialize this correctly and in the beginning everything is kind of semi-transparent, what happens is that every point along the ray is actually contributing to the color of the final ray. So the derivative with respect to any point along the ray is usually not 0. And then that allows for like a nice optimization. Does that make sense? Cool. And this is something I'm going into detail here because now we're going to change some of these things, and it's important to understand. So, okay, so like summary. So, for example, this gave rise to these neural radiance fields, right? This is a paper from 2021. Well, I also just realized I forgot to include any of the citations in the slides. I'm going to update the slides to have the citations at the bottom. So none of the slides today have the acknowledgements, which I have to fix. Okay, but like let's take, for instance, neural radiance fields. This is from Mildenhall et al. In 2020. What the idea here was is you take a neural network, right? It takes an XYZ coordinate, and then the other two things we can ignore for a moment. Those were these view-dependent effects, like the thing that allowed you to do reflections and stuff like that. So it takes an XYZ coordinate input, gives it to your neural network, and then it maps it to a color and the density. And then that allowed us, here you can see another visualization of the rendering process, that basically allowed us to define the color of a pixel as a weighted sum, as an integral over these densities and colors along the ray, right? Good. So what is a problem with this? Like the problem with this is that, of course, to render a single ray, you have to take hundreds or even thousands of samples, correct? So for instance, like this is kind of clear if you imagine that your scene has, like, for instance, a large depth range. Even in this room here, if you imagine you want to, like, you move the camera in between here, right, and you want to do a good job at rendering all of these chairs that are kind of constantly being occluded and disoccluded, you have to imagine that in order to do a good job at rendering, you need to make sure that there is a sample that falls, like you need to discretize the ray finely enough that a sample falls onto every surface that you want to render. The moment where you're like basically missing a surface, so which means that there is not a single sample along the ray that falls onto the surface, in that moment you can't do a perfect job at reconstructing the scene anymore. So in order to render the scene well, you have to take thousands of samples. So in many of these photorealistic scene representation, many in these photorealistic reconstructions, there's literally like thousands of samples. Now, what does that mean? In the case of our neural radiance field, it means that to just render a single ray, we have to do 1,000 forward passes through a fully connected neural network. This fully connected neural network in practice has to be pretty beefy. It's like 8 layers, 512 hidden dimensions, which means that just rendering a single ray takes an enormous amount of memory, and it takes an enormous amount of time. It's ultra slow. It's really, really slow. Let me give you an idea how slow exactly. So this is a neural radiance field, and this is rendering. So this is not optimization, this is rendering. So MIPNERV 360, which is a paper from 2022, renders on like I don't actually know which GPU this was. It was probably like an RTX 4090, or like a modern GPU. It renders with 0.07 frames per second. That's really slow. And you have to imagine that because rendering is also the process by which you fit, right? Like during training optimization, you have to render all of these images all the time. It gets even slower because now you have to do a forward pass with 0.07 FPS, and now you have to do a backward pass, which takes exactly as much time again, or potentially even more. So it's really slow. It's really slow. Optimizing like a large scene, like let's say, for instance, you have the scene here at the top. Optimizing a scene like that with a neural radiance field takes days on like state-of-the-art hardware. It's really slow. Okay. However, we already discussed a few ways in which you might fix this, right? We said, okay, why do you use a neural field? Like, why do you use a neural network? You could use other kind of scene representations. We discussed voxel grids. You can basically get creative with the representation that you use to parameterize the function, right? So, for instance, you could say use a voxel grid. That makes it a lot faster. You can do a thing where you have like a voxel grid maybe, but the voxel grid can't be that high resolution because it gets too big. So in order to have fine detail, you might do something like you have an additional hash function that like takes a point. We didn't discuss this in detail, but there's like other tricks that people have done to speed this up, and they basically come down to having some kind of discrete representation and then also having a little neural network, and they basically work together via these hybrid representations. Do you remember that? Yes, good. Okay, excellent. So this works, and it speeds up things drastically. So here, this is a paper from NVIDIA, Instant NGP, Miller et al. From 2021. And Instant NGP now renders at 9 frames per second. So this is optimized like a lot. Like these are literally people at NVIDIA. They wrote everything in custom CUDA code, like really fast, as optimized as it gets. But still, 9 frames per second is not very fast. It's certainly very far away from anything that you can use in real-time computer graphics, right? If you want to play a video game, 9 frames per second is not going to cut it. You need more like 60 or 120 FPS. So we're very far from that. Okay, good. So now we're coming to an interesting observation. So we discussed these different ways of parameterizing functions, like parameterizing 3D scenes. So far, all of the things that we discussed were assuming that we're parameterizing our 3D scene via these dense fields, so like these volumetric representations that map a value to every 3D location. Every 3D location in space can be mapped to a density or color. So right this year, some 3 months ago, there was a paper that came out that took a different approach, and we're going to discuss that paper now. That paper is called 3D Gaussian Splatting for Real-Time Radiance Field Rendering. This is the front page of this paper. It was written by folks at INRIA, which is basically the Federal Research Institute in France. The institute is actually at the Côte d'Azur. It's right in Nice, which is a very, very lovely place to do research. And this is the front page of the paper. And just looking at the title of the paper, right, you can already kind of figure out what's going on. So the important part is real-time radiance field rendering. And let's see. So this is a scene from the MIPNER from a data set. So this is a ground truth image. And the important number is right here. Hours rendered with 93 frames per second. MIPNER 360 rendered with 0.07 frames per second. So this is 3 orders of magnitude improvement in speed. So how did they do that? Okay, here it is plotted again. So like this is the same plot that I showed you earlier. So these are these 2 radiance field parameterizations we talked about so far. And then this paper, Gaussian Splatting, basically went from 9 frames per second to 170 frames per second, which is quite significant. Okay, so what's the key idea? The key idea is to say, well, what does a neural radiance field do? Or like a voxel grid, it doesn't really matter. It takes a 3D coordinate and maps it to an RGB alpha component and does that at every point in space. You're storing information for every point in space, including all of the empty parts of space, right? So, which means that in this room, for instance, there's all of this empty space, and you're storing information for the empty spot. But not only are you storing information, you're also always traversing that when you do rendering, right? When you do rendering, even though there might be nothing along the ray, you shoot this ray into nothingness, you still have to compute this integral. You still have to sample 100 or 1,000 points along this ray just to, in the end, render basically nothing. Or like the ray might hit that wall back there, so like 90% of your samples are spent on rendering nothing, 0 density, and then you hit the wall back there, and that's the only time you get a sample that actually tells you anything. Okay, that seems a little stupid. Can we do better? And some of this might seem obvious, but we're going to discuss later why it's maybe not that obvious. So the key idea of this paper is to say, what we're going to instead do is we're going to parameterize our radiance field sparsely, so we're only going to store information where the density is non-zero. Specifically, we're going to parameterize our radiance field via 3D Gaussian blobs that are floating in space. So here I'm drawing 2D Gaussians because I can't draw very well in 3D. But what does that specifically mean? It literally means that you're parameterizing your radiance field by like just little 3D Gaussians that are floating in space. And each Gaussian, the density of the Gaussian at every point will give you literally the density. So that's going to be the opacity, the density of the radiance field at that position is going to be given by the evaluating all the Gaussians that are floating in space at that point. And the color at that point is going to be given by the color of the Gaussian. So each Gaussian is now going to store a color and the density. And the Gaussians can be stretched, so they can have like 3D full covariance matrices. So like they can be ellipsoids. Okay, so specifically the density anywhere in space where there is no Gaussian is basically vanishingly small. If you're sufficiently far away from the Gaussian, the density is going to be 0. As you get closer to the Gaussian, the density obviously increases. So actually, this is these densities are you might choose to normalize your Gaussian in different ways. So like the density need not be 1 at the highest level. You could have that as a free parameter. What is the density of the Gaussian at the mean of the Gaussian? Okay, so this is actually what this looks like. So what this could look like, this is actually a video from the paper. Here on the right, you can actually see what these Gaussians look like. So here's a scene. You can see these blades of grass in the foreground. And you can see that these blades of grass are actually represented by one big ellipsoid. Right? So this is actually, what you're seeing here is actually a scene that is rendered with the algorithm that we're going to discuss in a moment. So on the left-hand side, that's not ground truth. That is actually the rendering, the differentiable renderer running on top of these Gaussians. And on the right, you can just see a visualization that shows you what the underlying Gaussians look like. So this is basically, I think what they're doing here is they're just shading the Gaussians. So they're basically using Phong shading or some other shading algorithm that we discussed before. Instead of drawing the Gaussians with like a fuzzy density, they're just saying we're going to draw each Gaussian as an ellipsoid, which basically says like 99% of the density are contained in this ellipsoid, and then we're just going to shade them, and this is what it looks like. So this is the way that you have to imagine the scene representation looks like. Any questions so far? Straightforward, I guess. Great. Okay, now next, how to render this. And now it gets a little interesting. So how do you propose we could render this? If I told you, okay, we have a radiance field, right? So it's actually the same as in your radiance field before, right? We have a radiance field now. It's just a function that maps every 3D coordinate in space to a density and a color. So what would be a renderer you might propose for rendering this? Oh, no. You didn't see that. Yes?
On the ray, just go to like the mean.
Good. Good. So you gave the smart answer, which is almost correct. But I was looking for the dumb answer. Actually, now I have to give it myself. It's obviously not the dumb answer. It's the obvious answer, I should say. What's the obvious answer? The obvious answer is, well, you have the same scene representation, so you're going to render it with the same integral, right? So like the same, clearly you're parameterizing the same function, so clearly you can use the same volume rendering integral. And that is indeed correct. You could absolutely go ahead and you could run the same volume rendering integral that we before did for NURFs. So you shoot a ray, define a near and far plane, and you sample points along the ray, and then you compute this integral. That would absolutely and totally work. And in fact, what would you expect would you expect this to be fast, slow? What do you think? Yes?
I would think it's slow
because well, you don't have to compute intersections. You would just evaluate each Gaussian like naively. You would take all the Gaussians. Let's say you had 1 million Gaussians in space, and at every point along the ray, you would have to evaluate all 1 million Gaussians. That would, of course, be like really slow. But in practice, of course, you don't have to do that because the contribution of each Gaussian like vanishes extremely quickly. So in practice, what you could, for instance, do is you could go ahead and say, okay, for this ray, which Gaussians do I actually have to consider? And you could easily reject like almost all of them, right? You basically take the ray, and then you say, okay, I'm only considering Gaussians that actually have none, like it's pretty cheap to test which Gaussians are like along this ray. And then you would have to evaluate not that many of them. So in fact, this would be not that bad in itself. Like I think you could probably make this reasonably fast in itself. So you could. So this would basically probably get close to like instant NGP or the voxel grid that we just discussed, maybe in complexity. But actually, I'm not sure. It could be that it would be very slow. I'm actually not entirely sure. But basically, you could use the same rendering algorithm that we discussed last time. However, now comes the slightly smarter algorithm, this slightly smarter answer. Of course, we're still sampling lots of empty space. Like we're still doing this thing where we're sampling lots of points along the ray. That's probably stupid because we know already up front where the density will be non-zero. And like you gave the first order answer, the first order answer is you know where the means of the Gaussians are. So if I tell you where the means of the Gaussians are, it would at least be easy to say, okay, there's like in all of this space, there's nothing. So certainly I don't have to sample any points along in this space. Okay. And now we're going to go through some properties of Gaussians that will allow us to define a really, 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 really fast rendering algorithm. And this is like some not so obvious thing. And this is like lots of math that I copied from existing papers. I would rather have this be a discussion with you guys. So like the key idea here is we're going to go through this math actually this is some math that was you and Hans-Peter Pfister's lab. So actually Hans-Peter Pfister is a professor at Harvard. This very equation here is copy-pasted from Hans-Peter Pfister's paper from 2001. So this is your advisor here at Harvard. Yeah. So Matthias Zwicker is the first author. Hans-Peter Pfister, I think, was the second author. He was a postdoc at the time, maybe. And then he's probably not going to recognize. No, don't show him that. I forgot the citation. Okay, great. So you can tell him I said hi. Or you can take a picture, but tell him that I forgot the citation. I'm going to add it in the final slides. Okay, so this is actually copy-pasted from that very exact paper. The name of the paper is, I forgot it, but it's like something volume. I think it's called Splatting for Volume Rendering. I'll add all of this on the slides that you can download online. Okay, so let's go through a few properties of Gaussians that are going to help us formulate a really fast rendering algorithm. And these are actually non-trivial, and they're really cool. So we're not going to derive them here. I'm just going to tell you about them. What you see here is just the parameterization of a 3D Gaussian in vector notation, right? In matrix vector notation, right? So you basically say a 3D Gaussian at mean p, so like a 3D Gaussian centered around a point p, is given by this equation, which is basically, right, you have 1 over 2 pi times the covariance matrix V, which is a 3 by 3 matrix, times exponential, and then I'm sure you've seen this before. Who hasn't seen this before? Good, everyone has seen this before. Okay, otherwise I would be concerned. Good. Next, so here, now it starts getting a little bit, well, this is probably also still obvious. So the point of the slide is Gaussians are closed under a set of operators that we're going to exploit. So what does closed mean? Who knows what closed means? A set being, yes?
That if you apply that operator, you get something back in the same set.
Right. Gaussians are quite special because Gaussians are closed under lots of operations. So Gaussians in particular are closed under affine transformations, and they're closed under integration, which is like absolutely not under all integration, sorry. They're closed under integration along an axis specifically. So what does that mean? So if you apply an affine transform to the input coordinates to the Gaussian, the thing that you get out in the end again is, you were giggling. Do I have a mistake on my slide?
No.
Okay, good. Please tell me if I do. I'm going to giggle with you. But so Gaussians are closed under affine transformations. This means if you have an affine transformations of coordinates, so like for instance, phi of x equals mx plus p, where m is a 3 by 3 matrix and p is a 3 vector. And this could also be expressed as a homogeneous thing, right? Remember, blah, blah, blah. But we're not doing that here. Then if you apply this mapping phi onto the input of the Gaussian, then the thing that you get out is again a Gaussian floating in space. It's going to be a Gaussian that is going to be deformed, basically. So basically what ends up happening is you're basically going to translate it, and you're going to change the covariance matrix. Make sense? Okay, good. So here's something that is non-obvious. I haven't derived it myself. Didn't have the time, but I would like to do that. It's probably quite fun. So this is really non-obvious. It means, what you see here is saying we're going to be integrating our three-dimensional Gaussian, so G3V. V is the covariance matrix. 3 means it's a three-dimensional Gaussian, along the axis x2, which is meant like x0, x1, x2 is the 3 dimensions of the input. So if you integrate a Gaussian along one of the axes, then what comes out is again a Gaussian. And this is something that is non-obvious, and it's quite special. So Gaussians are closed under integration along one of their axes. So the thing that you get out is, in fact, a 2D Gaussian. So when you integrate, which makes sense, you're basically projecting out, and maybe you already see how this might end up being useful. You're basically projecting out one of the axes, and when you project out one of the axes, it turns out that you get out a 2D covariance matrix. And it turns out the 2D covariance matrix is actually you drop the third column and the third row of the 3D covariance matrix. And that, in fact, gives you the covariance matrix of the 2D Gaussian. So far, so good? Good. Okay. So now we're just going to use this to build a little rendering algorithm, okay? Specifically, what we're going to do is we're going to project our 3D Gaussians onto the image plane, more or less. So basically what we're going to do is we're going to derive. Well, we're just going to do it. Sorry, I haven't gone through this. This is the first time I'm talking about this, so like we'll try to do it together. So who remembers what a cam-to-world mapping is? I hope everyone. Yeah, cam-to-world, right, was this thing that took like a coordinate in, well, world to cam is the one that we're using here, is like a coordinate in world coordinates takes it to a coordinate in camera coordinates, right? So imagine we want to now render the scene parameterized by 3D Gaussians. We're placing our camera in space. Our camera is defined by the intrinsics and the extrinsic parameters. The extrinsic parameters being the world to cam or cam to world matrix, which basically tells you the orientation of the camera and the position of the camera in space. And now we want to basically ask, what is this camera seeing in this cloud of Gaussians? The first step we're going to take is we're going to take all of our Gaussians, which are living in 3D world coordinate space, and we're going to transform them into camera coordinate space. And that just means you're applying this affine transformation with the world to cam matrix, basically. So let's do that. So basically, this is exactly what we just did. So our cam to world transformation is just an affine map. So we just apply the affine map to the input of the Gaussian. Does that make sense? Good. So we're just transforming our Gaussians. Now, what would be the next step if we wanted to render? If we wanted to render something, always we did the first thing, we transform it into camera coordinates, and then what do you do next? You project it onto the image plane, right? So the next thing we're going to do is we're going to compute the projection. So we are asking now, okay, we have all of the Gaussians in camera coordinate space. Now we're interested in what is basically the footprint of each of these Gaussians on the image plane. So we're going to project each of the Gaussians. Now, the problem is that ideally what we would like to do is we would like to use the same trick again. We would like to use the trick that the Gaussians are closed under affine transformations, or ideally what we would like is that the Gaussian is closed under projection. But that would be ideal, right? So if you take the projection mapping, which is, if you remember, it's this K, it's just like the multiplication with the intrinsic matrix plus the Z divide when you convert it from homogeneous to heterogeneous coordinates, right? That shenanigans. Ideally, what you would like is that when you have a 3D Gaussian and you first transform it to camera coordinates and then you project it onto the image plane, ideally what you would like is that that operation, the final step, also keeps it a Gaussian. Because if it would keep it a Gaussian, then you would just have the expression of the Gaussian as it lands on the image plane. Unfortunately, that mapping is not an affine mapping. What does that mean, it's not an affine mapping? It just means it's not a linear plus offset map, right? So, and you remember, if you remember correctly, this is kind of what the homogeneous coordinates kind of fixed, right? In homogeneous coordinates, projection was an affine map. It was which means it was just parameterized by the intrinsic matrix, right? Unfortunately, at the end of the day, we really need to sample our Gaussian with a 3D coordinate. The homogeneous coordinates don't help us. We really need to compute the projection. And so the projection, if you remember correctly, this is just a different way of writing out the projection matrix, the projection operator. So mu is the projection. So it takes a coordinate, and then it divides it by z, and it has the homogeneous, like the scalar value one. So this is ignoring the focal length, but it doesn't matter for now. Like this is kind of the this is assuming focal length is 1, basically. So this is basically just a general projection operator. Does that make sense? Okay, so this is the projection operator. Unfortunately, Gaussians are not closed under projection. What does that mean? It means that if you now take mu, and you just, what we would really like to do is we would like to take this mu, and we would just like, again, apply it to the input of our Gaussian, such that we project our Gaussian, and then ideally we would get out another Gaussian. Unfortunately, that's not the case, because Gaussians are not closed under non-affine transforms. So here's a really cool trick. The trick is we're going to approximate this mu via its first order Taylor expansion. Does everyone know what a Taylor expansion is? No? No? Okay, actually, I'm not going to derive it because I don't trust myself driving it right now. I'm going to definitely make a mistake. But basically, the Taylor expansion is basically approximating okay, maybe I'm going to give this a shot. Please, someone correct me. I haven't explained Taylor expansions to anyone ever, I don't think. So imagine you have a function. This is a function f of x, and you have a function x, and you have the input x. And now you would like so this function here is nonlinear, right? It's not a linear function of x. But now you would like to approximate this function in some neighborhood. So for instance, you take this x coordinate here, x1, and you would like to have a linear approximation of the function at this coordinate x1. And it shouldn't be too surprising. The way you can get that is basically just saying, okay, we're going to take the tangent or the derivative of the function at that point. That's just in the 1D, that's just the, how's it called? The incline? No. Slope, thank you. The slope. So you just get the slope of the tangent is like the slope of the line that goes, the slope of the tangent of the function at that point. And then you just have the offset, right? The offset of and so now you can at this coordinate, you can linearly approximate this function. And so the Taylor expansion is a generalization of that, but a first order Taylor expansion is basically doing that. And this is exactly what you can see here. So you take this projection operator, and you're going to say, well, the projection at a coordinate u can be approximated by some offset xk. Then this Jacobian uk, which is just like the derivative in 3D, it's like the tangent this is just the derivative 3D times the delta. So basically, anyway, does that make sense? Good. Okay. So we just have basically what we've done is we have just linearly approximated our projection operator by an affine transformation. This transformation is affine. So now we're in luck because we can see, okay, this is an affine transform, so we can just stick it into we can just now stick it again into the same equation that we had before. So because it's an affine transform, the same equation applies. And it turns out now we can get an expression for the 3D Gaussian after the projection operator. And now one thing that is maybe a little bit confusing is when we talk about projection operators, usually we say that the projection is taking us from 3D to 2D. In this case, the way in which this is meant is slightly different. Actually, what we have done is we have our camera, which is a perspective camera like this. And what this step actually, and like imagine now our 3D Gaussians would be like floating in space here. And actually what we have done by doing this step is we have applied a transformation to our Gaussians that puts them into this space where all of the rays are parallel. So we have basically warped all of the Gaussians such that now the rays are parallel, and this is and we basically have just warped the Gaussians. Does that make intuitive sense? So previously the Gaussians were there. Now you warp the Gaussians according to this equation that we just had. And what will happen is basically that the covariance of the Gaussian is going to be warped exactly by some factor that is the linear approximation of the projection operator. So long story short, what it means is now this J here is exactly the Jacobian, like the derivative of the projection operator at the 3D coordinate that we're interested in. W was the W that we got from the covariance matrix that we got from the cam to rho transformation, from the rho to cam transformation. And now this is the new 3D Gaussian. So now we have an expression for each of the 3D Gaussians if they were in this space here. Does that make intuitive sense? Any questions? I don't think I did an amazing job at explaining this, so please feel free to ask questions, and we might all understand it better. Yes? Yeah, we're not yet at the orthographic projection, but that is a yes, actually that is a good, yeah, this is a good way of thinking about it. Like one way of thinking what we have just done is usually we don't think about this, we usually don't think about projections with this intermediate step. But in fact, what happens is if you do the way you just described it is a viable way of thinking about projections. It's basically saying, okay, we take our camera, we place it in space, we have a 3D point, we transform it into camera coordinates. And now what this whole z-divide projection operator does is it's basically stretching, it's taking apart the rays and it's making them parallel. And then afterwards, getting the projection of the point is just an orthographic projection, which means you just set one of the axes to 0, if that makes sense.
But this warping is an approximation.
Yes, in this, so yeah, so I think the image on the left, I'm not sure if this was computed with this approximation, but yeah, this warp is an approximation. So like it's an affine approximation, yes.
So that's why like the splatting.
Good question. So splatting, yeah, so what does splatting mean? Splatting, the idea of splatting is basically, what inspired this word is, I think, that you have an image plane, the camera has an image, and you take the Gaussian and you splat it onto the image. So it's like a paintball. You splat it onto the image.
Okay, but then how do you do with depth? Like with the cover, if you're doing layers? So
Yeah, good question. We're not there yet.
Okay.
Coming up in a second. Very good question. So just so far, do these steps make sense? I mean, it's like so far it's just arbitrary, like random math. But now comes the magical. So long story short, all we have done now is we have gotten an expression for the covariance matrix of the 3D Gaussian in this weird space, which is basically in the space where the rays are parallel. In that space, we can basically parameterize the Gaussian via this 3D covariance. And why is that important? This 3D covariance is just computed via matrix products. It's just dot products. There's nothing weird here. This is basically, this is extremely fast. This is just like 5 matrix products. Like this is basically free in terms of compute, right? Okay, good. So now comes the magical part. Gaussians are closed under integration along one of the axes. So the Gaussians are now in this space, And now all of the rays are aligned with the forward vector of the camera, basically. All of the rays are parallel, aligned with the forward vector along the camera. So now it turns out that Gaussians are closed under integration, which means there is an analytical expression for the integral of the Gaussian density along the ray. Okay, let me repeat what that means. It means now that we had a Gaussian in 3D space. We have our camera. And remember, what we want in the end is in volume rendering, we are computing this integral of the density along the ray, right? We're computing this expected value of the color and the density along the ray. And previously, because there was no analytical expression for the integral along a ray, we had to do this sampling mumbo jumbo. So naively, if you wanted to integrate the density of the scene along the ray, you could do it by a quadrature. You sample all of these points along the ray, then you get the density of this Gaussian under all of these samples, and then you compute this weighted sum that we discussed before. But now the magical thing is that we have just derived an analytical expression for the density of this Gaussian along this ray. In other words, what that means is there is no more sampling. Computing this integral can now be done analytically with just a bunch of matrix vector products. Okay, what does that mean? It means that now we can compute our volume rendering integral in the following way. What we're going to do is we're going to take our 3D scene that is like Gaussians floating in space. We're going to take a pixel. And now basically what you do is you do like one pre-processing step, which is which Gaussians have anything to do with this pixel at all. So you can basically ask, it's pretty cheap to like figure out which Gaussians have a likelihood of at least 99, which Gaussians influence this pixel at all. So all of the Gaussians that are unrelated to this pixel, you just throw away, right, as we discussed before. So now you basically have an expression for all of the Gaussians along the ray that have something to do with this ray. And now all you have to do is you have to make a list of all of the Gaussians along the ray. Now you're going to order that list by depth, which is all easy, right? Like this is all like matrix vector products. You take this list, you order it according to the depth of each of the Gaussians, with the closest Gaussian being first and the final Gaussian being last. And now you have an analytical expression for the integral of the ray through that Gaussian. So now you just go through the list, you evaluate that analytical expression for each of the Gaussians, you weight the color of the Gaussian according to that integral of the density along the ray, and now you just slot that into this weighted sum, into this weighted sum that we remember from volume rendering. Okay, let me put this in slightly different terms. This is in the end how we evaluate our color for the ray under volume rendering, right? And now it turns out that this previously this Ti and this alpha I we had to compute via these samples, and now the way you can think about it is that you don't have to take these samples anymore. You just have Gaussians floating in space, and for each of the Gaussians, you just know what is the probability that a ray will pass through the Gaussian or not. This is just analytical. It's just an analytical value that you can compute. And now each Gaussian has a color, and you're just going to weight the color of that Gaussian by that value, which is the likelihood that the ray has stopped when it has reached that Gaussian, and then you can compute the integral analytically. Does that make sense? Any questions? Yes?
So which part is that integral, like which part of this equation is that integral along the Gaussian doing?
Oh yeah, great question. Thank you. So we discussed that so it's this part. It's basically this third property that we're exploiting here. It's this property that the integral of a Gaussian along a ray. So this is the integral of a Gaussian along one of its axes. In this case, it's the x2 axis. Is just the same as taking a 2D Gaussian and evaluating it at that point. So like this is a great question because I didn't. Thanks. This is a very good thing that I didn't explain. So what ends up happening is you have let's say you have this Gaussian here, and if you look at the image, it's kind of a little self-explanatory. So let's see, this is our camera, right? This is the image plane. So now if you can imagine that projecting this Gaussian onto this thing gives you this third property that we just discussed basically tells you that on this image plane there exists an ellipsoid that is the projection of this 3D Gaussian. So if I would draw this image, imagine this was actually in 3D, so there's a camera here and there's a Gaussian floating in space. If I draw that image, let's say the Gaussian would be like covariance like that, then you would basically get a 2D Gaussian that looks like this. And now it turns out that the integral of the density, like let's say we look at this ray here. Say we look at this ray here. This ray might be this pixel here, for instance, right? So the integral of this 3D Gaussian along this ray, of the density of this 3D Gaussian along this ray, can be evaluated by evaluating this 2D Gaussian at this pixel coordinate. So you literally take this 2D Gaussian that you get via this derivation, and now you just put in the 2D pixel coordinate. And that is now you have computed the integral. So you just computing the integral is now equivalent of deriving what the Gaussian looks like after projection, and then just evaluating the 2D Gaussian at the correct point. Great question. Yes?
If you have multiple Gaussians along one ray and you want to render them,
yes, they need to be sorted by depth.
And is that something that is
Great question. This is you can consult the paper for details on this. This is done in the GPU via an algorithm that is called fast radix sort. So I mean, this is honestly the first time that word has appeared since I have taken an algorithms intro class in like 7 years ago. But radix sort in GPUs, GPUs do this all the time. Radix sort, for instance, the same process that is being used here is basically also used to render meshes. So yeah, maybe this is another piece of information that I'll include in the next iteration of this class. When you render a mesh, when you render a scene represented by meshes, you basically end up doing the same thing. You shoot your ray, you figure out which triangles this ray intersects, and then you just sort the faces by depth, and then you throw everything but the first one away, basically. And then you take the color of that first one. Or unless it's transparent, in which case you would do the same. Exactly. So what you end up doing is you basically you sort them by depth, and then you go down the list, and for each of the Gaussians, you basically get its density along the ray. And for the first Gaussian, what is the contribution? Yeah, let's go through this briefly. What is the contribution of the first Gaussian to the color of the ray? It's going to be exactly that integral times the color, right? But what's the contribution of the second Gaussian? The contribution of the second Gaussian is this expression that we have seen before, which is basically 1 minus the density of all previous Gaussians times the density of this Gaussian, because that's the probability that the ray has stopped at one of the Gaussians before, and then that's going to be the weight of that Gaussian. And basically, you will end up going down this list until this 1 minus thing is going to be 0. Basically, until the integral of all the previous Gaussians that you have seen until the probability that the ray has stopped is 1. And then all of the other Gaussians you don't have to look at anymore because they're being occluded by the Gaussians that come in front of them. Does that make sense? Other questions? No questions? If I quizzed you on this, you would all. Okay, good. Let's see. So yeah, actually, I even made slides for this. So, okay. So there's this operation called a culling. Let me just unskip these slides. I mean, I made slides for this is maybe an exaggeration, but in practice, what it looks like is when you render. So these slides were meant to illustrate what this actual algorithm that you end up implementing on the GPU looks like. And this algorithm has a bunch of tricks. And I'm going to tell you some anecdotes about that in a moment. But basically, what you literally end up doing is you take the camera, you get the pixel, And now the first thing you do is you compute the so-called pixel frustum, which is basically each pixel has like basically boundaries, right? It's like a little square. Each pixel is a little square or a little rectangle. And so you can basically compute these bounds of the pixels. So each pixel is basically a cone, and it's called a frustum. This geometrical object that you get is called a frustum. So the camera frustum is basically the cone that you get if you unproject the boundaries of the image, and the pixel frustum is the cone that you get when you unproject the boundaries of the pixel. And then it's very cheap computing the likelihood of the Gaussian, of the likelihood of this half plane under any Gaussian. That's really cheap. So you can do that for all the Gaussians in your image, basically. So even if there's a million Gaussians, it's really cheap to say, okay, this Gaussian is outside this frustum, like 99. Okay, so that's really cheap. So you do that, and then you do the aforementioned ordering stuff. So then you basically, this ends up, like the GPU ends up giving you a list of all of the Gaussians that you haven't thrown away. And now you literally do this radix sort where you get the depth of each of the Gaussians, you order them according to their depth, and then you exactly loop, like you have literally a for loop on the GPU that loops through this list of Gaussians and computes the contribution of each Gaussian to the color of the final pixel. Yeah? What is this slide? Yeah, whatever. Yeah, so here's a little visualization of what it looks like. This is what I had hand-drawn poorly. It turns out that if you have like Gaussians that live on a surface, like you have a surface like a plane, and there's a Gaussian on the surface, and then the same is true. You can also project this 2D Gaussian onto a 2D Gaussian in the image plane, and the same property is true that it also again gives you a 2D Gaussian. And so this is what you see here. So for instance, there's this 2D Gaussian on the surface of the plane and of the sphere, and on the surface of the sphere, it's actually an isotropic Gaussian. So it means it's like a round. It's a rotationally symmetric Gaussian. But after projection, it turns into this ellipsoid because the Gaussian was like flat, right? Yes.
How do you decide how many Gaussians to place in it?
Aha, now we come to the great question. Good. This brings us to a question. So we just described how we now can compute this integral, the volume entering integral, as exactly as we had done it before, but now it's much cheaper. Do you see any problems with this? From anything you've learned so far, how would you now actually go about reconstructing a scene with this knowledge? What have we just done? We have described a parametrization of the radiance field, right? And we have described a differentiable renderer. Okay, so I haven't actually told you that this renderer is differentiable yet, but you can just take my word for it. I mean, you can also look at all of the operations we just did, and all of the operations we just did are matrix products and stuff. And the sorting doesn't have to be differentiable. Because what are we trying to optimize? We're trying to optimize the color and the position and the covariance matrix of each of the Gaussians. Those are the free parameters. We have a million Gaussians, and we're just optimizing the color and the position and the thing of each Gaussian. And everything we just discussed is differentiable with respect to these parameters. So, okay. So now, how would you actually go about doing reconstruction with all we've discussed so far? Like, I'm going to give you a, yes? Yeah. Exactly. So okay, I give you 1,000 images. Each of the images has camera parameters. You take your scene. You take your scene, which is parameterized by 1,000 Gaussians that are floating in space. You don't know anything about the scene yet, so you randomly initialize them, right? And now you just, because this render is differentiable, you just code it up in PyTorch. That's not actually what you do. You code it up in CUDA because it has to be really fast. And then you just press go, and your little atom optimizer is going to just optimize the parameters of each of the Gaussians to fit the pixels that you have observed in the images, right? And then you just run the algorithm. Do you foresee any problems with this? Yes?
I think it's similar with this, like, I guess, having the Gaussians like wall around during optimization.
Yes. Did everyone hear that? Yes, that's exactly the problem. I think two of you alluded to this earlier, so good intuition. The problem is exactly local minima, right? And like, let's be very specific about this. Like, what does that mean? It means that, like, imagine you had two images, like these two images here. And these two images, let's say this image here looked like this. Okay, now I have to think about how that actually looks like. Okay, I don't trust myself drawing it right now. Imagine that you had your two images, and now in order to fit both of the images, what would have to happen is that a Gaussian would have to move through space to like let's say there was a green Gaussian in space, and that green Gaussian would want to move to a green spot. Actually, yeah, you know this example already. Remember the example that I talked about with the ball, where the ball has to move, right? In the image plane. Do you remember that? This is literally the problem we have right now. It's basically exactly that problem, where we have a Gaussian in space, and the Gaussian has to move in order to generate an image. But there's so many problems that it could run into. For instance, let's say the Gaussian is currently green, and in between the Gaussian, on the image plane, there's something that is blue. The Gaussian is never going to move through the blue area because it would increase the loss. So its gradient descent is not going to do that. The Gaussian is never going to move through the blue area of the image. And so your Gaussian that should move is never going to move. It's just stuck in place. So the problem is if you try to optimize this, you initialize a bunch of Gaussians randomly, it's not going to work. Okay, so this is what so this is what the authors actually do. What does SFM mean? Structure for motion. So like the old call map hits again. So you take all your images, and someone asked a question when we talked about differential rendering. So what you literally do is you take the images, you reconstruct them with call map, and call map gives you these sparse depth maps. It basically gives you like approximate depth maps. And the first trick you're going to do is you're going to not randomly initialize your Gaussians. You're going to put them at the depths that are predicted by call map. So trick number one. So now the Gaussians are already approximately at the right spot. But of course, there's still many things that might go wrong. Okay. So then what we're going to do, so projection, adaptive density control, this is basically just the adaptive density control is exactly the thing we're going to talk about now. There's a second step, a second trick. The second trick is actually that you're going to implement a heuristic that is going to spawn Gaussians and destroy Gaussians as the optimization goes on. So basically, it's a pure heuristic. There's like no, actually, literally, if you read the paper, it's like, this is what we came up with. It makes a lot of sense. We figured out this hyperparameter when we should spawn a Gaussian and when we should destroy a Gaussian, and it turns out that works well. So literally, what you do is you initialize your Gaussians according to your structure for motion point cloud. Then I think you initialize a bunch of other random Gaussians floating in space. And then what you do is you run optimization for like some fixed number of steps. That's a hyperparameter, some heuristic. Let's say in the paper they're like 100 steps. We run optimization for 100 steps. Now all of the Gaussians are going to wiggle a little bit in space. They're going to stretch. They're going to change their color. They're going to change their density. And then every 100 steps you run your little heuristic. And what is the heuristic going to do? It's going to set all the Gaussians that have the density set to 0, like that are transparent. It's going to throw them away. Done. Don't need them anymore. And then it does something. And then it's basically it's using some criterion to say this is a part of space that we have underexplained. We have a big Gaussian that is trying to explain like a big image feature. We're going to split that Gaussian into two. Or you have spaces where there's too many Gaussians, and at those points you're going to merge it. And what is the criterion you use? The criterion they use in the paper is they take view space positional gradients. So what they do is they use the differentiable renderer. They render the point cloud. And now they're going to take the gradient of each Gaussian relative to its position. So they ask, how much does my optimizer want to move this Gaussian? And this is a pure heuristic. They're basically saying, we have observed that in the areas of the image that are currently not well explained, the gradient of each of the Gaussians with respect to their position has high magnitudes. And there's some intuition behind this because, of course, why would your Gaussian have a large gradient with respect to its position? It's because in that area of the image, those pixels are poorly explained currently, which gives you a large loss for those pixels. And the only way that the optimizer can do this is it can only move the Gaussian or like change its density and so on. And they basically found that the gradient of the loss with respect to the position of the Gaussian is a useful heuristic to decide when to split and when to merge Gaussians. Yes?
This seems counterintuitive to our reasoning about before in regards to like stuck in local minima, because if you're stuck in a local minima, your gradient is 0. Position of the function.
Yeah, that is a good point. let's think about if that's actually true. If you're stuck in a local minimum, would the gradient be small? So the loss would be large, but yeah, you're right. Like at least with respect to the intuition we had discussed earlier with respect to the ball moving, which necessitated the multi-scale loss. With respect to that, I think you're certainly true. You're certainly correct. I think the way to maybe think about the Gaussian part is that the Gaussian is fuzzy already, right? So it's kind of like you had already blurred your image, and now so you do have a gradient, and that gradient, like imagine, yeah, I think it's a good question. I don't know the answer. Maybe the one piece of intuition would be if we go back to this example of our balls floating on this on this plane. If you take this loss, if you wouldn't blur this image, you're exactly correct. Then the gradient of this loss relative to the position of this ball is 0, because if wiggling the ball around doesn't lower the loss, so the gradient is 0. But we discussed you can blur it, and when you blur it, then the gradient is non-zero. And the case of the Gaussians is the case where you have already blurred the image because the Gaussian is fuzzy. So you have blurred this image, and so you do get a gradient, and that gradient is probably large. But good question. I'm not entirely sure. Yes. Yeah.
Like, will the heuristic pruning and will it get rid of the little dots or merge it into?
Why would it merge them? Why? Yeah.
I guess my question, so you said the Gaussian blobs are but if in a scene representation.
Good question. So, yeah, this is a great question. So, it will generally it won't be disregarded as long as it shows up on the images, right? As long as it shows up in the images, it contributes to the loss. Like, let's say, for instance, you had a tree with little lightning bugs floating around it, right? You have a big sphere or something. I don't know. Actually, looks like one of these graphic scenes from the 90s, like these demo scenes. Like imagine you have a big sphere and there's a bunch of tiny lightning bugs floating around it. The lightning bugs definitely generate, you can see them on the image, right? Even though they're small. So it definitely won't disregard them because each of them is going to generate an error in the image plane. So even if they're very small, each of them is contributing to reducing the error. And as long as, so generally no. Does that kind of answer the question? Cool. Yes. How do you initialize? So they initialize them generally with structure for motion. So they basically take the means of the Gaussians and they place them at the positions of the Gaussian. Oh, sorry, you mean when you split them? Yes, great question. When you have a Gaussian and you split it, then indeed what they do is they interpret the Gaussian as a probability distribution, and they sample from that probability distribution twice, and that gives them 2 new locations. And then they actually have a little step. I don't have it on the slides, but then they basically initialize the densities of these 2 Gaussians such that their volume integral is going to give you the same as if you took the volume integral of the one big Gaussian that you just had to start off with. But they set it to the same color as the Gaussian that they split.
Okay.
Yeah, good question. And then when you merge them, I would guess it's take the mean or something like that. Yeah. Cool. Yes.
I think you mentioned this way back earlier in the slides, but each blob, I know it has a single color. I think you said it decays away from the center, right?
Yeah, it has the same color for the entire Gaussian. Yeah.
I asked because also in that picture, it looks like it's kind of the colors fading at the edges.
Yeah, I think it's just transparency. It's transparency versus the background. Yeah, but good question. I also asked myself if it's just transparency. Yeah. Yeah.
Also, I was just noticing in the thing they set the threshold for large gradients to 0.0002, and so it seems like they're not actually that big when it's.
Right. I don't know what large or small gradients mean, but yeah, you're right. It's just random, right? They just picked it and they were just like, hey. Okay, so here's a little bit of fun stories, 2 fun stories. George, who's the first author on shared first author on this paper. He gave a talk in my COOP meeting. It was a great talk, and he had a few funny anecdotes. The first, he had a piece of advice for anyone who wants to do this kind of research. He said, and this seems obvious, but like always write a lot of visualizations. So whatever you do, he said the biggest progress in their project was when they wrote an interactive visualizer of this, like basically an interactive renderer. Right? It's not enough to write a renderer. When you have the renderer, then you can give it parameters and you can press go and it gives you the image. But they basically wrote an interactive UI with which they could just interactively interact with the scene. And you could look at the scene while it was being optimized, right? Because the optimization is really fast. And they said that the moment they started doing that was the moment where they started making the biggest progress. Because you can really zoom in and you can really literally look at a single Gaussian and you can see what it does. And you can build these toy experiments where you have an assumption of what should happen and then you just look at what happens. Like looking at what happens is one of the single most important things in research. Like if you, so whenever you're stuck, usually the two pieces of advice that I give people is make the problem simpler. Don't make the method, like if something isn't working, don't make the method more complicated, make the problem simpler. That's the first piece of advice for researchers. And the second piece of advice is when something doesn't work, always write a lot of visualizers, like try to visualize every aspect of the problem. Okay, so obvious. The second piece that is funny is that the person who implemented this, both of them are experts on fast real-time rendering. So the first author on this paper, he is a little CUDA wizard, and George shared the story that basically every week in their weekly meeting, that guy would come to the meeting and was like, I made it twice faster. And he did that for 3 months. And so at the end, it was really fast. So, right, like, okay, good. So there's not that much more to talk about. I think we are kind of... Okay, so here's what this optimization looks like. This is a scene where they didn't initialize the Gaussians with the structure for motion initialization. Turns out that that's not necessary. It just makes it a lot faster and it helps. But here they just initialized them randomly. So at initialization, they just initialized all of the Gaussians to be gray, and then they just made them float around in this like unit cube around the object. And then here's what the time lapse looked like. So you can actually see, my guess is every time it like pulsates, that's probably one of these 100 steps where they reinitialize the Gaussians, where they split them and merge them. And here is just a bunch of visualizations. So these are all scenes reconstructed with this framework that we just discussed. These are, if you do research on this stuff, then these are all scenes that you have seen before. So this was something that was really popular in the early 2000s for novel view synthesis for this kind of problem. Back then, this is a recent scene from 1960. So these are not videos. Well, these are obviously videos, but these are not real-world videos. These are renderings from the reconstruction. So these are all views that weren't in the training set. And like, it is really quite impressive, right? Like literally, these scenes are photorealistic. Like if you look at them, unless you look like really closely, you can't tell that they're not videos. So this is really cool. So this is literally something that has happened now. So this is new. 10 years ago, this was impossible. 10 years ago, some people would have told you that's science fiction. And it was, in a way. Actually, so this is just the video from the paper that I placed just for all of the cool visualizations. Let's jump ahead. So yeah, here's a few comparisons. So MIPNERV 360 is a neural radiance field approach with a hybrid scene representation, voxel grids, and Instant NGP is also voxel grids with a hash map, and you can see that you get all these floaters. Aha. So intuitively, right, like these floating artifacts that you get, it makes a lot of sense why the thing that we're just discussing might not have any more floaters, right? So floaters happen in like neural radiance fields because your neural network is this continuous function, and when you backpropagate into one part, like into one point in the scene, then like you wiggle around, all the parameters of the neural network wiggle a little bit, and then it might make another part of the scene have non-zero density again. Or more generally put, it's really hard to make the output of your neural network go to exactly 0. That's like really hard. But it's very easy to just not place a Gaussian at a part of the scene, or to basically just define a threshold and say, oh, I'm deleting all the Gaussians that have a density that is lower than this and that, right? Yes? Yeah, great question. So I think if you have a foggy scene or mist, then I think in principle, if it was just blurry, then it would probably be fine. Then you would just could have like a bunch of Gaussians that are kind of floating. But certainly if you have crisp smoke, I guess that you might be better off doing it with an actual dense radiance field. Or you would need a lot of Gaussians, which is fine. In fact, in video games, oftentimes I think it is literally done with particle-based simulations. So smoke in high production value movies, I think is actually done with particles. So you have the smoke cloud is 1 million particles, and then you do volume rendering of this particle cloud. So literally what you do is you take these particles, and then you have a set of differential equations, or some hacky computer graphics thing that kind of looks good enough that that tells you how the smoke will move over time, and then you just do volume rendering. Cool. So this is actually kind of the end of the lecture. So to wrap up, we now finished the differentiable rendering part. So we talked about graphics a little bit, just as a high-level overview of how physics-based. Yeah, one quick note: this is still not physics-based rendering, right? In the sense that this thing does not deal with reflections. It does not deal with view-dependent effects in a principled way. So this thing doesn't have materials, for instance. Again, we talked in the classical computer graphics thing, we said that surfaces are represented as surfaces, and then they have this BRDF, or the spatially varying BRDF, which basically tells you how the surface is reflecting incoming light. None of this is happening in this representation. This representation does not have a notion of light bouncing around in the scene. Instead, each of the Gaussians is emitting light. Each of the Gaussians is a floating, glowing little orb, and that's it. And so these scenes, as you might be able to tell, they do actually sometimes have view-dependent effects. You can see reflections, and the way these reflections are done, again, exactly as in neural radiance fields before, are done by each of the Gaussians not just storing a color. Okay, sorry, I should have made. Now we're making it slightly more complicated. But actually what each of the Gaussians is storing is a little function basis for, it's actually storing a little function that tells you if you look at this Gaussian from this angle, that's the color you're seeing. And it turns out these functions, the function basis that you use here are spherical harmonics, which is basically, you can imagine just a Fourier basis for functions on spheres. Does everyone know how Fourier series work? A Fourier series, yeah? Okay, Fourier series is just a weighted sum. You parameterize a function as a weighted sum of Fourier coefficients, right? And each Fourier function is just, each basis function is just a little sign, right? And spherical harmonics are the same thing. You can do the same thing on the sphere, and you can imagine you just have basis functions on the sphere, and then you can parameterize functions on the sphere as a weighted sum of these so-called spherical harmonics. So actually what each Gaussian is storing is a set of weights for this basis basis of functions on the sphere. And that allows you to just say that if you look at this Gaussian from this angle, it has a different color than if you look at this Gaussian from this angle. But these colors are varying very slowly. So these functions aren't very high frequency functions, so they don't have any fast changes in color. It's more like if you look at the Gaussian, it'll slowly change its color over time, if that makes sense. Does it make sense? Okay. It's also not that important, but just so that you have heard about it. Yeah, so in other words, if you see these scenes having a reflection, it doesn't actually have a reflection. All it does is it'll store in the Gaussian, if you look at me from this angle, I look like that. But it doesn't actually simulate how light bounces off the Gaussians. Okay, so here's a few more reasons why this is a cool paper and why people are very excited about this. You can't escape it these days. One reason is that this representation is actually very close to the representation that we use in conventional computer graphics for meshes. Meshes are rendered in a very similar way than we render this. It's almost the same. What that means is that you can buy a plug-in for Unreal Engine right now that just imports any of these scenes in Unreal Engine, and you can render it in real time in the in-game engine. And that's a really big deal because you couldn't do that before with these neural radiance fields. That was not possible. But now it's possible, and that's really cool. And so I guarantee you, when you play a video game in 7 years, in 5 to 7 years, you will play video games where some of the 3D assets in the video game are going to be parameterized as these Gaussian splats. And from the perspective of the video game developer, that's amazing, because they are just okay, I want to put a Ferrari in my video game. Usually now you have to go and send someone off to maybe model the Ferrari by hand, or you send someone off to scan the Ferrari with all of these like age-old tools that kind of suck, and then it's going to give you something that kind of looks like the Ferrari, but then you have to like polish it up. Not anymore. Here, you just take the thing. It literally runs on your iPhone. There's an app called Luma, which is done by some of the folks who wrote some of the papers that we looked at before. You download the app, you like scan the Ferrari with your mobile phone, and boop, there's the photorealistic Ferrari, and you can drop it into your video game. So reasons why that doesn't work right now is because you can't relight it. Because this thing doesn't actually simulate light bouncing around in the scene. It turns out if you want to take your Ferrari and you want to put it in dark New York at night, then you really need the Ferrari. You really need to be able to like have the light bounce around. Otherwise, it'll look garbage. It'll look like you took the picture in California. It doesn't look like you took it doesn't look like the Ferrari is standing in New York City at night. So that's one big problem. So these things, they can't be relit right now. So that's one big challenge. But who knows? I guess that I know that a bunch of people are working on this. Maybe that'll change soon, but we don't know. Okay, so here, just to start for you to think about like some other stuff. And now we're starting to get more, from now on, we're going to get more machine learning. So now we said we are moving to differential rendering. So now it's everything we discussed so far was, like in the past few lectures, was in the differential programming framework. But as you can tell, there was no actual artificial intelligence in any of this. There were no neural networks, or if there were neural networks, it turned out they actually basically just did fancy interpolation, which maybe, okay. So now here's the little toy problem. Imagine, so the thing we discussed so far is this thing where you can just have lots of images, for instance, of this toy car, and then you can fit the toy car using differentiable rendering, yay. Or you can do it for real-world scenes, right? Like we discussed it for real-world scenes, so we have nailed this now, great. Okay, so now we're going to make the problem a little harder. What if I only give you one image of the scene? If I give you only one image of the scene and you run any of the algorithms we just discussed, what do you expect to happen? Yeah, it'll fail. How will it fail? Oh, yeah. Sorry. You go.
I was going to say, you'll probably be able to render that image, but you're going to get like points along the rays.
Exactly. Exactly. There's no multi-view. In a single image, there's no 3D information, so there's no way for you to reconstruct the 3D scene. Like in a single image, in this case, if you don't know how cars look like, there's no way for you to reconstruct the 3D scene given the single image. But in reality, the thing that you do in your head all the time is much closer to this than it is to any of the other things we just discussed. In particular, if I enter this room, I haven't seen the back of that chair back there, ever. And yet, I probably can't imagine how this chair looks like photorealistically, but yet I know really well what the 3D geometry of that chair looks like, right? I can imagine what the 3D geometry of the chair looks like. And in fact, if you manipulate objects that are lying on your table, you never have this case of full information about the 3D scene. You always have incomplete information about the scene. You never see all of the perspectives of one object at a time. And more so than that, you also never get complete information about many of the properties that actually, even about the properties that are participating in light transport. Let me give you an example. Sorry, I said we would stop, but I lied. We will stop in a moment. Actually, this is a bad example. I'm looking for some object that is, yeah, this is good. Okay. Here's an object. What is the color of this point? Yellow, good. Okay, so you're obviously right. The color is indeed yellow, but this color is completely different than this color, right? Because in fact, there's lighting, and because of lighting, this color here, in fact, if I took a picture of this right now from here, and I take a picture from this box of things from here, the two colors are completely different. They have, they're both yellow, fine, they're both yellow, but they're actually completely different. But it turns out when you talk about objects in your real life, when you talk about colors of objects, just like you did it right now, you always talk about what humans talk about as the material color. You basically usually you identify the thing that you're seeing by the material that it's made out of, by the BRDF, in other words, by basically the parameters of the BRDF, rather than by the actual color that you're observing, because you don't care about the actual color. There's no way, like unless you're an artist that has to photorealistically draw this box, in which case it matters a lot if you get the color right or not. Generally, it doesn't matter if you get the color right or not. But what is very impressive is that if I change the color of the light right now, this box might not be yellow anymore, and yet you would still know that the color is yellow. because you have learned something about the world, and your brain is actually constantly using the things you have learned about the world to complete all of these parameters of the objects around you that you can't actually observe. So even though your brain can't possibly, like, I don't know, your brain, for instance, I see a reflection of this exit sign back there right now in the window. And in fact, the number of observations that I have of the scene are not sufficient to figure out what the geometry of that reflection of that exit sign is. Because to do a good job at that, I would need to capture thousands of images because there's so many degrees of freedom. There's a reflection. How far is the window away? Like, what's the color of the background? What's the color of the foreground? Like, how far is this thing away from that thing? Like, there's so many degrees of freedom that your brain is just constantly filling in just by learned experience, basically. And this is what the rest of this course will be about. The rest of this course will be about how can we use the tools that we just discussed to actually train neural networks to discover, to learn about properties of the 3D world such that you can solve this problem. I show you a single image of this car. How can you reconstruct this car from a single image? And then later on, obviously cars are not that exciting, toy cars. And then later on, I show you an image of a real-world 3D scene, or maybe I show you 2 images of a 3D real-world scene. How can you reconstruct the scene that is underlying these 2 images? Cool. Thanks for coming.